Hello, Flat Earth researchers, debaters and debunkers. With the help of this toy teddy here, we're going to look at two fundamental facts and physics of real life on this Earth that we have to ignore in order to perceive or believe that we live on a spinning globe. So first of all, before all of this, let's be very, very clear that what I'm going to show you is scalable. It can be done on any scale, across meters or miles, hundreds or thousands of miles if you like. It doesn't make any difference. The physics doesn't change. Now, it is well understood, of course, that a tabletop experiment like this is being done on a planet-sized Earth, and the model here is very much understood that if you live on a spherical planet with a lot of mass, it is that spherical mass that creates gravity or gives things weight on the Earth when we perceive the Earth as being in empty space whizzing around the sun. It is well understood that the direction of down when you perceive yourself being on a sphere is towards the center of that sphere. There is no problem in assuming that, which is what has to be done for the globe Earth model. If you look at the Copernican heliocentric model, what we had was a decision, not from any discovery, but just from a point of view to put the sun at the center and have the Earth going around the sun. Hence, the Earth was then referred to as another planet, and it was assumed that the planet Earth is spherical and has a certain amount of mass. So the model is understood, but what we're going to see is the application of real life physics and what happens in real life observations and how those are ignored or converted into this perception of us being on a spherical Earth. Now, what we have here is actually an external frame of reference that we have to kind of assume or imagine when we think about ourselves being on a spherical Earth. And again, when we think of ourselves being on a sphere, it is understood that wherever you are on that sphere is always going to be on top for you. The surface will always curve down and away from you in all directions. But of course what we have here is a flat surface, and it is a flat surface with an edge. So over here is physically lower than up here. Okay, so down here is a lower elevation, so this, we could assume that this is then some kind of curvature that goes off, and we'll end up with things being at a lower elevation. So here is our external view of the scene, which we have to perceive if we are going to imagine ourselves on any kind of Earth. First thing we'll look at is perspective. So if we then put ourselves into the same place as the teddy looking across the surface of the flat surface, we can make a couple of observations about how things have changed. Just to point out that the teddy's eye level is right here and the camera's eye level is down here somewhere. So what we have is a flat surface that appears to rise up to our eye level, the center of the camera's field of view. Even though this drops off right here, we have a horizon created by this flat surface, and this surface could go on infinitely. It wouldn't appear to rise up any higher than eye level if we have a horizontal line of sight looking straight across that flat surface. So what we have here is a horizontal line of sight for us that appears to meet this table edge here. So the table edge you would appear to be higher than the base of the camera. But of course we know that it wasn't when we looked at it just now from the outside. So I'm going to just put the pen here at the teddy bear's eye level. We can see that it's just about there. Okay, and now we'll bring the camera up slightly to see what the teddy bear would actually be seeing. And we can see that the horizon in front of us, even though it's very, very short, rises up to the teddy bear's eye level, because we are now at its eye level. So here we are making a height adjustment of just a few centimeters, and we can see this difference in how the horizon now appears when our camera level is at the same level as the teddy bear's eye level. All right, so this is scalable. You can try this anywhere you like. You can try it at 40, 50,000 feet if you like, and you will get the same results. The horizon for our eye level, the camera's eye level, will be right in the center of the camera's field of view. This tells us that the surface is level. We know it's not curved. However, we of course are taught to perceive that the horizon in front of us is either a bulge of curvature with a surface that rises up in front of us. All the while, we always know that that surface isn't physically as high as the bear's eye level here. We know that we have raised the camera off the table, yet the horizon in the distance appears to be at our level. So this is sometimes converted into curvature. We are told to believe that we see a bulge of curvature rising up in front of us. And the other thing we are led to believe or assume or even have faith in with this belief is that at the horizon, this is where the surface begins to curve down and away from us. So we might be looking across the sea or a lake, and we might see something that's passed off as curvature. For example, the pylons over Lake Pontchartrain that appear to curve as they get towards the other shore. Well, is that something that is just an optical phenomenon, or is it something that can be demonstrated practically with a side-on view? Let's go back to that side-on view a second and take in this scene again. So again, we have this line of sight from the teddy bear, which is parallel to the surface, the flat surface, but we know that those parallel lines will never physically meet. But in our field of view, they appeared to meet. The teddy bear wasn't looking down, okay? So again, we go back to those two scenarios of having us perceive that we're looking into some kind of bulge of curvature, or we're seeing a drop-off, the beginning of a drop-off at the limit of our field of view, or the vanishing point. So these two bottles are now at an equilibrium. The water is the same level in both the bottles, and this demonstrates to us that this table is in fact level. It started off with this bottle on the right being empty, and this one on the left had all the water in it. I started off the siphoning process, and eventually this bottle on the right filled up to have the same level of water in it as the one on the left. Now, there's a couple of things that we can note here, is that when this bottle was filling up this bottle on the right, the water had to go up and then it went down, but then it also had to come up again in elevation in order to fill up the bottle. So in that sense, you can say that water went uphill. It defied gravity to go uphill. But what will never ever happen is we'll never get the water maintaining the same level in both containers if the containers are not level. One thing we can do here is raise this bottle, and now that it's at a higher elevation, it will now fill up the bottle on the left. So we can see here that this has filled up and this has gone down by raising this to a higher elevation. So we can re-establish that equilibrium by doing the same to the other bottle. And if you leave them like that, eventually they will reach the same level. So again, this is a practical way of determining that the surface is level. The water in both these containers will fill up to the same level in each of the containers. Again, we understand, and it's no feat of the imagination to perceive that this surface becomes curved, and because we have this idea of the force of gravity coming out of the earth and going towards the center of said spherical earth, that level then becomes something different. But in our practical reality, it doesn't. We can imagine it, we can perceive it, but we cannot practically demonstrate a difference in level and have water continue to maintain a level. So again, if we go back to the lake scenario, we looked through this teddy bear's eyes and we saw that this was a horizon, so we have anything beyond that horizon being a lower level. So let's just go ahead and do that. Let's put this water at a lower level down the curve, beyond the horizon now that we saw, and down the curve. And of course you will see the water is flowing out of this one down to this one. Even though it has to go uphill, it will flow. And we can see now that obviously eventually, if this bottle on the right was further away and beyond a curve, it would fill up this container and this one would remain empty. So we've just seen two practical and scalable examples of facts of life, repeatable observations and physics, natural physics that does not change. However, when we are told to perceive ourselves as being on a spherical earth, we must believe that physics changes, or we must at least change the definition of words such as level. But as I said, this is scalable. These two containers can be hundreds or thousands of miles apart on the earth. The fact that I'm doing this on a tabletop with a massive earth creating gravity apparently beneath me makes no difference. The fact that something will fall through the air does not dictate that the earth is a sphere. It is just a measurement that has been used. The rate of acceleration has been used as a foundation for talking about there being a force coming out of this spherical earth. Of course, we have to imagine that because we know that otherwise it would be physically impossible to stick to the outside of a sphere. We have to invoke this idea of gravity because we know that it's physically impossible. Our practical daily experience and everything we do in physics demonstrates to us that we're on a level, stationary Earth. And that physics doesn't suddenly change just because you decide to look at yourself from outer space. The physics and the observations for the people on Earth do not change. So again, just to drive it home, when we perceive ourselves as being on a spherical Earth, of course there is no top and bottom to a sphere except where we are. We are then on top of that sphere. So the horizon is considered curvature, and it's considered that everything is curving down and away from us beyond the horizon. So it would be physically lower than us. It doesn't matter whether you're perceiving this as being a ball in outer space. The practical physics of this earthbound experience demonstrates to us that the idea that water can stick to the outside of a spherical Earth is a load of rubbish. It cannot be practically demonstrated, because if this was a curve and we put the bottle down here, the container down here, this water up here at a higher elevation will flow to a lower elevation, even if it's got to go uphill to do so. Yeah, and there we have this bottle now with more water than this one. Alright, so it doesn't matter where you do this. If one bottle, one container is higher than the other, then it will feed the container at a lower elevation. Simple physics. So if anyone wants to laugh and assume that someone doing an experiment like this is being ignorant, all you have to do is scale it up and show us water not flowing down a curve. Can anyone do that? Another observation we can take away from this is to show how easily observations using water levels and trying to line them up with the horizon can be manipulated to say that there is some kind of drop that doesn't line up with the water levels. Well, you can see here that because the camera's eye level is below both of these water levels, we have a level here that appears to be higher than this level here. Yeah, if I just pull this out, we can see what appears to be this big difference in the level of the water. But that is simply because of perspective. When we bring it over here, we can see that they are both in fact level. But when we take it to this perspective, this bottle now gets further away, so it appears smaller. So the level of water compared to this one appears to be lower, but it isn't. We know that actually physically it is the same height. It all changes based on perspective. So here we have what is demonstrably and measurably level, but here we have an observation that tells us, if we don't take perspective into account, we will believe that this is higher than this one further away. Simply not the case. So of course when people try to line these up with the horizon, they end up doing all sorts of things which puts everything out of whack. As we saw just now, a few millimeters or centimeters will make a difference to the apparent level of the water. And then of course we can manipulate it to have the horizon appear to be lower than the water level. But it's only when we look at it from this perspective that we can see that they are in fact level. So again, this is why perspective is the imaginary curve. Thank you very much.
Click subscribe and the bell icon if you'd like to receive notifications of new videos from Phuket Word.